Welcome to our talk SailfishOS Forensics. My name is Krassimir Tzvetanov and I'm a graduate student at Purdue University. I'm a dual degree student focusing on digital forensics in my PhD and homeland security for my master's. I'm also a research assistant at the CyberTap program. CyberTap is a program designed to assist local businesses in the state of Indiana with their IT and cybersecurity needs. On the agenda today, we have a quick introduction to SailfishOS and its evolution, methods of acquisition, analysis, and forensics artifacts, which will be grouped in four major categories: telephony, wireless interfaces, system, applications, and we're also going to look at future work we intend to conduct in this space. Introduction to SailfishOS. Sailfish is a relatively new Linux-based operating system for mobile devices. Originally, it was developed by Jowa Oi, which was founded by ex-Nokia employees. Its primary target is embedded devices such as smartphones, smartwatches, tablets, and IoT devices. The company has gone through several rounds of funding, latest being Round C in 2016. It also operates using regional OEM licensing scheme. The product is adopted in Russia under the name of Aurora OS. The main driver for development and adoption of the operating system is the need for independence from the US-based Android and iOS. This is also the only approved mobile devices for government use. The Russian government intends to deploy 8 million units by the end of 2021. In addition, in the past, the Ministry of Communication of Russia has provided grants for developers who port their applications to the operating system. The principal developer at this point in Russia is Open Mobile Platform, which is currently owned by Rostelecom. Sailfish comes from a long lineage of operating systems for mobile devices, starting back in 2005 with OS 2005 designed for the Nokia Tablet 770. Later it evolved into MIMO, which was used on the Nokia N900, and later it was merged with Moblin for the Nokia N9 and was named MiGo. When Nokia sold to Microsoft, the project was spun off as an open source project called the Mer project. SailfishOS is the open source Mer project codebase combined with proprietary user interface developed by Jowa Oi. There has not been a lot of forensic work done in this space. The only work pertinent to SailfishOS was posted back in 2016 to Forensic Focus. There's also some work done on the other platforms, but most of it is not pertinent to the new SailfishOS. In this talk, we're going to outline the different discoveries we made when investigating SailfishOS. First, we'll start with acquisition and analysis with commercial tools, then we'll look at the partition schema, and then we're going to show the different artifacts discovered in several major categories. This section covers acquisition. We attempted both acquisition with commercial tools and open source tools. The commercial tools used for acquisition were Magnet Axiom Process, Celebrite UFED, and Mobile Edit. None of those tools was able to extract image successfully. Just for completeness, we decided to test those tools in analysis after the image was acquired using twerp. None of those was able to analyze the content properly, and only Autopsy was able to extract individual files, but it was unable to read any of the schema and make any meaningful assertions and conclusions about call logs and so on. Acquisition with twerp was performed not without a problem. Initially, we attempted to use the backup and ADB interfaces, and both of those failed. However, we were able to use the ADB shell and then the DD tool to make a complete image of the phone. Later, this image was analyzed using SleuthKit, and we were able to extract individual partitions and files. As all transfers were conducted through USB, here is a summary of the time it took to perform some of those operations. The USB interface itself is interesting as it presents with different minor number depending on the state of the phone. For example, when it is in bootloader mode, the minor number will be 0DDE, and when the operating system is running or the phone is charging, it will be 0AFE. In developer mode, this changes to 0A02 because the device is also going to expose a network over USB interface, which will be seen as a RNDIS interface on the operating within Sailfish itself. The configuration for the USB port are stored in varlib USB moded INI and have the following structure. You can observe the local IP address of the device in this file. The partition schema is a bit particular. It has over 80 partitions, and most of them are organized in AB schema, which allows for one of the sites to be upgraded while the other is untouched. So if there's a failure during the upgrade, the phone will still be able to boot with the alternate side. This section outlines the methodology we use to analyze the device. The methodology is pretty straightforward. We acquire a baseline image of the device, then introduce targeted changes to particular subsystems and record the time at which those were introduced. Then acquire another image of the phone and compare it to the baseline. The differences will show how the changes that were introduced changed the file system and the state of the device. This process was repeated a number of times, and in later stages we also used a shortcut by secure shelling into the phone and observing the files changed as we were introducing the changes through the user interface. The test hardware platform used was a Sony Xperia XA2. This is a single SIM device running the Qualcomm Snapdragon 630 chipset. The SailfishOS version itself was 32120. This section outlines the forensic artifacts pertaining to telephony. SIM card information is stored in the Telephony DB SQLite database. You will notice that most of the data and settings in this operating system are stored in SQLite databases. SIM card and carrier properties are in different tables as shown below. You can observe the ICC ID in the SIM info table, as well as the MCC and MNC. Similarly, in the carriers table, you can see a list of carriers. Calls and text messages are stored in the ComHistory DB file. One of the fields designates the type of the event, whether it's a phone call or an SMS message. The table also contains information about the start and end time of the event, and the direction, 1 for incoming, 2 for outgoing. Last but not least, text messages have content which is recorded and stored in the free text field. During a forensics investigation, it is extremely important to understand if multiple SIM cards have been used within the same device. Even more, it is important to understand when certain messages were received and what SIM card they were sent to. Within SailfishOS, we can find this information into tables. The first one is the table events, which records the incoming events like calls and text messages, and the table event properties, which would give us the ICC ID of the SIM card being in operation at that point. Those two tables bind based on the ID field in the events table and the event ID field in the event properties table. Furthermore, when using multiple SIM cards, it is good to understand when a SIM card was first introduced to the device and when the user stopped using that particular SIM card. The oPhono package manages all SIM card functions. Its settings are stored in the varlib oPhono directory. Within that directory, we will observe subdirectories for each SIM card inserted. For each one, you will find two. The first one will give us the timestamp of when the card was initially introduced to the device, and the second one will give us a timestamp of when the card was last used within that device. Furthermore, the directories will contain a GPRS file which will hold the settings that came with this particular card, like the APN, for example. They will have multiple contexts. In this particular case, context 1 is used for internet access and context 2 is used for MMS. As already mentioned, the oPhono package manages all telephony subsystem functions, i.e. the data link layer. The network layer is managed by the connection manager, which settings can be found in Home System varlib conman. Once a new data context is activated on the device, Connection Manager will create a subdirectory named cellular ICC ID context number. In this particular case, we observe cellular 310.260 context 1. In this configuration file, we can also observe the name of the cell phone provider, the time when those settings were last changed, as well as the IPv4 and IPv6 addresses of the device. Based on the timestamp of this directory, we can also make another couple of inferences. We can see when data was last enabled on this device, which means that if the user has disabled data and then enables data without swapping the SIM card, we can register that change, as well as we can see when the data was shut off by the timestamp on the history home hour file. This section covers the artifacts pertaining to wireless interfaces. As previously mentioned, all network layer connectivity is managed by the connection manager, and its settings are stored in Home System varlib conman. Within this directory, the settings file represents the state of the different subsystems. If the phone is switched to airplane mode, the offline mode variable within the global section will be switched to true. Similarly with GPS, Wi-Fi, cellular, and Bluetooth sections. The Wi-Fi MAC address can be found in the data vendor Wi-Fi WLAN MAC bin file. All configuration pertaining to the device will be stored in the Connection Manager directory in a subdirectory named after that MAC address. To be more precise, the name will be Wi-Fi_MAC address and then some additional data which is specific to the network that the device is connected to. Within that directory, there will be a stats home file which will contain additional data pertinent to that connection. In this particular case, you can see the SSID, the name of the network, and the IP address that was assigned to the device. You can also see the timestamp of when this configuration file was last modified. The Bluetooth interface similarly has its MAC address located in data vendor Bluetooth. However, it also has this value in varlib Bluetooth, where the rest of the Bluetooth settings are stored. In this particular case, our device has a MAC address that starts with D4, so the configuration settings are stored in directory varlib Bluetooth, D4, and so on settings. The settings file will tell us if the device is currently set to discoverable, if there's a timeout for it being discoverable, and also what is the name of the device. For all paired devices, there will be a subdirectory based on the MAC address of the paired device. In each of those directories, there will be an info file which will contain additional information about the paired device. In this particular case, we see that this is a headset. We can see that it is trusted, so it can read the address book from the device. And we also see the link key. This section covers forensics artifacts pertaining to the system. During a forensic investigation, it is important to understand when a particular device's timeline starts. In other words, when the device was set up and first used. Upon initial boot, SailfishOS will prompt the user to go through a setup wizard. As a result, a couple of files will be created on the file system which can help an investigator infer when the device was first set up. In addition, the last boot time is stored in the last boot time UTC file, and based on its timestamp and contents, this time can be determined. Last but not least, every time the system boots, it creates a file called system_boot timestamp, and this file contains information on the kernel and other important information used during boot. Unfortunately, only the last two copies of this file are preserved. However, it is possible to carve those files from the file system and recover other times when the file system has been booted, and maybe discover that one of those times an alternative kernel was used and as a result of a malware infection or some other kind of intrusion on the device. All user accounts are stored in the accounts database file. This file contains a number of tables, and some of them will contain the account names, some of them contain services that are that those accounts are bound to, and some of those tables contain settings. All credentials are stored in the sign-on secrets DB file. This file contains unencrypted plaintext passwords and tokens. During forensics investigation, it may be necessary to establish if other people had access to a particular cell phone and if it was protected. A factor in establishing this proof may be the state of the device lock of the phone. SailfishOS allows for the user to set a PIN or use fingerprint to unlock the device. If a PIN is set, its hash will be stored in the device lock ENC file. Furthermore, the device lock settings configuration file will store a timestamp of when the PIN was set. If a PIN is not set, then the device lock inc file will have length of 0. If fingerprints are set, they will be stored in the Sailfish FPD templates userdb file. This will be the content of the actual fingerprint. However, the existence of configured fingerprints will be reflected in the fingers.json file, which will also contain the time of enrollment of the fingerprint, and it will also be reflected in the index CSV file. The system maintains contacts and address book, which are both stored in the contacts DB file. This file has a large number of tables that reflect different properties of a person. Some of them are email addresses, some of them are addresses, and contact information. Now, there is a table called deleted context, which unfortunately doesn't seem to be containing any deleted context. So currently it is under investigation if this table is an artifact left from past functionality or if it is a future development. This will be covered in our future work. Since there are multiple tables that split a record in different areas, all of them are tied using the contact ID field. So all records pertaining to the same contact will have the same contact ID field. This section covers forensics artifacts pertinent to different applications. The first application we cover is the web browser, which is a version of Mozilla. Its settings are stored in Home Nemo Mozilla Mozembed. The cache of this browser is stored under Cache 2. All certificates are stored in the Key4 database, and some of the logging information is also stored in logins.json. This can help us assert that particular user has access to particular website because we have the authentication credentials to that website. In addition, the trusted certificate store is stored in the cert9db file. It is important to note that unlike the desktop version of Mozilla, this one has a fairly limited set of root certificates, which overall increases the security of the device. Last but not least, the cookies file is called cookies SQLite and stores cookies and browsing history. In addition, the HSTS sites visited by the user will leave a trace in the site security service state.txt file. The email application is a derivative of Qmail, and all of its settings are stored in Home Nemo QMF. The email bodies are stored in QMF/mail, and each message is stored in a separate file. In the case of multi-part email messages, there is also a subdirectory with the suffix parts created. In this particular example, we can see this message has multiple parts. We can see the content type there, and then this message will have a subdirectory with the same message name -parts created, and within that directory you will see the different parts of that MIME message. The rest of the settings are stored in the Qmail store DB file, and there is a number of tables there that contain this. The calendar application stores its data and settings in the mkcowdb file. This file has a number of tables, and all of them connect using the component ID field. Last but not least is the gallery application. All of the images on the phone are stored in three particular directories: Home, Nemo Pictures, and then Camera, Default, and Screenshots. This section covers future work and conclusions. While this research answered a lot of questions pertinent to SailfishOS, there are still few artifacts that we would like to explore. In addition, we would like to do a comparative analysis between Aurora OS and Sailfish. In addition, Sailfish can run Android applications using the Dalvik engine. In one of our future works, we're going to look at how different applications installed within that engine leave fingerprints on the system that can be used for later analysis. Last but not least, all of this work can be automated, and we'll work on automating the extraction of forensics data from the SailfishOS device. If you have any questions, or if you would like us to conduct specific type of research, feel free to contact me at krassi@purdue.edu. If you would like to get further details on some of the work presented today, you can also look at our article in Computers and Security named A First Look at Forensics Analysis of SailfishOS. We would like to thank everyone for attending this talk. We briefly introduced SailfishOS and why it is important for forensics investigations. We looked at the software evolution of the platform and previous forensics work done on it. We presented a number of findings grouped in several larger categories. At the end, we presented our plans for future work in this space. Thank you.